Have you ever wondered the nature of spacetime and gravity? It's a question that has intrigued and puzzled some of the greatest minds in science for centuries. Let's take a moment to delve into this enigma, to explore the intricate dance between these two fundamental concepts of our universe. Imagine spacetime as a vast, invisible fabric stretching out in all directions. It's not something we can touch or see, yet it shapes the way we experience reality. Objects with mass, like our planet Earth, cause this fabric to curve. This curvature, this warping of spacetime, is what we perceive as gravity. Now visualize a marble rolling along this curved fabric. It follows the curve not because of an invisible force pulling it down, but because the fabric of spacetime itself is bent. This is the very essence of Einstein's theory of relativity, a revolutionary concept that fundamentally changed how we understand gravity and spacetime. It tells us that gravity is not a force in the traditional sense, but a curvature caused by mass. This theory, as profound as it is, only scratches the surface of the intricate relationship between spacetime and gravity. Over the years it has faced numerous tests and challenges, and while it has withstood most, there are still mysteries that remain unsolved. For instance, how do quantum mechanics, the rules that govern the smallest particles in our universe, fit into this picture? Can we reconcile the macro world of spacetime and gravity with the micro world of quantum particles? The answers to these questions continue to elude us, hinting at deeper layers of reality yet to be uncovered. And this is where the excitement lies, in the pursuit of understanding, in the relentless exploration of the enigma that is spacetime and gravity. But could there be more to spacetime and gravity than what Einstein's theory suggests? As we venture further into the realms of quantum mechanics and relativity, we might just stumble upon answers that will redefine our understanding of the universe. The world of physics is split into two realms, quantum and classical. This divide has been a long-standing puzzle in the scientific community, and it is where our journey takes us next. Let's start with the basics. Quantum physics, the more mysterious of the two, deals with the world at an infinitesimally small scale. It's the realm of atoms, electrons, and quarks, where things can be in two places at once, and particles can be entangled over vast distances. Quantum mechanics is a bit like the Cheshire Cat from Alice in Wonderland, elusive and full of paradoxes. On the other hand, classical physics is the physics of the everyday, the macroscopic world that we can see and touch. It's the physics of apples falling from trees, planets orbiting the sun, and cars accelerating down the highway. It's the world as described by Newton's laws and Einstein's theory of gravity. It's predictable, tangible, and intuitive. Where the divide becomes apparent and indeed problematic is when we try to bridge these two worlds. Quantum mechanics and general relativity, Einstein's theory of gravity, have been like two languages that describe the same reality, but don't seem to understand each other. The equations of quantum mechanics are probabilistic, while those of general relativity are deterministic. The former deals with uncertainty and probabilities, the latter with certainties and absolutes. Scientists have been wrestling with this divide, trying to formulate a theory of quantum gravity, a theory that can describe the universe in a unified way, from the tiniest particles to the largest galaxies. Yet despite brilliant minds and countless hours spent, this quest has proven to be exceedingly difficult. It's like trying to fit a square peg into a round hole. The pieces just don't seem to fit together. For decades, the quest for a theory that unifies quantum mechanics and gravity has remained elusive. But as we'll see in the next scene, a new theory is rising to the challenge, promising to bridge this quantum classical divide and revolutionize our understanding of the universe. Scene script: enter a groundbreaking new theory that aims to reconcile these two disparate worlds. In this tantalizing turn of events, a novel hypothesis has emerged from the churning cauldron of scientific deliberation. It boldly suggests that spacetime, the very fabric of our universe, is classical, not quantum. This idea is nothing short of revolutionary, as it challenges the very foundations of modern physics. So, what does it mean to say that spacetime is classical? In simple terms, it implies that spacetime behaves more like a smooth, continuous fabric, rather than a choppy sea of quantum particles. It's akin to comparing a serene lake to a stormy ocean. This new perspective of spacetime brings with it a host of fascinating predictions and implications. One such prediction is the concept of larger spacetime fluctuations. Picture this: instead of the tiny, almost negligible quantum fluctuations we're used to, this theory suggests that spacetime experiences larger, more significant undulations. These fluctuations are not just theoretical musings, they could have real observable effects on the world around us. For instance, they could potentially impact the weight of objects. Recall that weight is essentially the pull of gravity on an object. If space-time is experiencing larger fluctuations, then the strength of this gravitational pull could vary, leading to changes in an object's weight. Imagine a world where a 1 kilogram bag of sugar doesn't always weigh 1 kilogram. This theory is certainly a departure from conventional wisdom, but it's an exciting one. It's like opening an entirely new chapter in the book of physics, filled with intriguing questions and uncharted territory to explore. Of course, like any groundbreaking hypothesis, this theory demands rigorous testing and scrutiny. We're at the precipice of a scientific journey that might reshape our understanding of the universe and its fundamental laws. This new theory could potentially revolutionize our understanding of gravity and space-time. It's an exhilarating time to delve into the mysteries of the cosmos. Who knows what we might discover next? But how can we test this revolutionary theory? That's the burning question on everyone's mind. The beauty of science lies in its ability to question, probe, and validate. It's not enough to just propose a theory, it must be rigorously tested. And that's exactly what we intend to do with this new theory that unites Einstein's gravity with quantum mechanics. One of the proposed experiments to test this daring concept is deceptively simple: measuring a 1 kilogram mass for weight fluctuations. You might think, well, a kilogram is a kilogram, right? Not so fast. If this theory is correct, then space-time isn't a quantum entity, but a classical one. This means that larger space-time fluctuations could occur, which would impact the weight of objects. Imagine for a moment that you're holding a 1 kilogram weight in your hand. According to classical physics, that weight should remain constant, right? But if space-time is subject to larger fluctuations, that weight could subtly change. It's a small difference, but one that could have monumental implications. This proposed experiment is just one of many. Other sophisticated experiments might involve observing cosmic phenomena or testing the behavior of particles in high-energy environments. The objective remains the same: to challenge our understanding of gravity and space-time. Remember, this isn't just about proving a theory right or wrong, it's about pushing the boundaries of our understanding, about challenging what we think we know. It's about the thrill of discovery, the pursuit of knowledge, and the sheer joy of understanding the universe a little bit better. The road to scientific discovery is often paved with trials, errors, and even failures. But it is through these experiments that we inch closer to the truth. These experiments could potentially confirm or refute this groundbreaking concept. Either way, the results will undoubtedly lead us to new questions, new theories, and new discoveries. After all, that's the beauty of science. It's an endless journey of exploration and understanding. These experiments could potentially confirm or refute this groundbreaking concept. The time has come to put this theory to the test. Will it stand up to scrutiny, or will it crumble under the weight of empirical evidence? Only time and rigorous scientific testing will tell. What would it mean if this new theory were proven true? Let's delve into the implications of this revolutionary idea. Primarily, it would redefine our understanding of the universe. The theory suggests that space-time is classical, not quantum. This shift in perspective would change the way we perceive not just gravity, but the fabric of our universe itself. It would mean that space-time is not a passive stage where events unfold, but an active player influencing the course of those events. The implications for quantum research are just as profound. This theory predicts larger space-time fluctuations which could impact the weight of objects. This might seem like a minor detail on the surface, but it has the potential to revolutionize how we approach quantum mechanics. If proven, the theory could bridge the gap between quantum mechanics and Einstein's theory of gravity, resolving one of the most stubborn paradoxes in modern physics. But the repercussions of this theory extend beyond the realm of theoretical physics. It could have practical applications that we can't even begin to imagine today. For instance, if the theory is correct and we can measure these space-time fluctuations, it could lead to new technologies and tools. Picture a future where we can manipulate space-time to our advantage. It could revolutionize fields like computing, navigation, and even energy production. But remember, these are just possibilities. The theory is yet unproven. And even if it's validated, further research will be needed to fully understand its implications. However, the mere fact that we're considering such a radical concept is a testament to the boundless curiosity and ingenuity of the human mind. It's an exciting time to be a part of this journey. Every new discovery, every shift in our understanding, brings us one step closer to answering the fundamental questions about our universe. What is space? What is time? What is gravity? As we venture into the unknown, the possibilities are as vast as the universe itself. Subscribe to our channel for more cosmic updates, where each discovery propels us further into the mysteries of the universe.